This tutorial is designed to give some insight into piecewise defined functions. I'm going to give some piecewise functions, and I'm basically going to teach it just by doing some examples. In order to be able to work these piecewise functions, you have to already know how to graph absolute value functions, quadratic functions, and in this particular case, rational functions. And so I'm not really going to give a tutorial over those, but I'll kind of explain a little bit about what I'm doing. This graph is broken into two pieces. One part of the graph, this rational function, is going to be used everywhere except where x is equal to 5. Except where x is not equal to 5. If x is equal to 5, I'm going to get a separate value apart from the rational function, and that's the value 4. And so looking at this bottom equation, 4 when x is equal to 5, I know that the value 5, 4 is going to be on my graph. The rest of the graph, from negative infinity to 5 and from 5 to infinity, is going to follow this rational function, x squared minus 25 over x minus 5. When I'm working rational functions, I always like to factor first. X squared minus 25 is a difference of squares, so I'm going to write it as x plus 5 times x minus 5. I have one point of discontinuity, setting x minus 5, the number or the expression in the denominator, equal to 0. I find that my point of discontinuity is at x equals 5. Because that factor is also found in the same degree in the numerator, they can end up canceling out for any x value that is not 5. And the rest of my graph just looks like the line x plus 5. That's not very hard to graph. I have a y-intercept at 5, and I have a slope of 1, so I'll continue to go up 1 over 1. I'm going to have a hole right here at 5, and then I continue on. Now, because I don't draw very well, I'm going to try and put a couple extra dots to guide me, and use your imagination and pretend that I drew a line with slope 1, y equals x plus 5, that just has a hole at 5, 10, but that's okay. That hole was actually covered in the domain by the point 5, 4. So what is the domain of this graph I have just done? Once again, the only x value that I couldn't use in the top was 5, but it got used in the bottom piece, and so my domain is all reals. What is f of 5? I think we already decided that f of 5 was 4. What is f of negative 1? Well, it looks like at negative 1 I should get 4. Let's check and make sure. Negative 1 is not 5, so it belongs to this equation. If I plug in a negative 1 squared is 1. 1 minus 25 is negative 24. Negative 1 minus 5 is negative 6. Negative 24 divided by negative 6 is equal to 4. So sure enough, f of negative 1 is equal to 4. Okay, I want to find the zeros of the function. I just lost my domain. Let me put it back real quick. Whoa. My domain is all real numbers. To find the zeros of the function, looking at my graph, that's why I like to go first. Clearly, the bottom one is not going to have a 0 because it only has one value, and that is 4. If I were to set this rational function equal to 0, remember that it's really x plus 5 everywhere except at the value x equals 5 itself. So I'm going to let the numerator x plus 5 be equal to 0. That tells me x is equal to negative 5. I must have a 0 at negative 5. Negative 5 equals x. The y-intercept I can find by plugging x, 0 in for x, into the equation that actually uses the 0, which in this case is the upper equation, the one that's not equal to 5, and I'll get negative 25 over negative 5, which is 5, so my y-intercept is 0, 5. I've already sketched the function. What's the range? Well, this line takes care of every point except this point right here. This hole, remember, was at 5, 10. It appears that I'm never going to get a y value of 10. I can get any other y value in the whole world except 10, so I'm going to call the range x is not equal to 10. We could say x where x is an element of the reals. X is not equal to 10. Is this function continuous for all real? Well, it is up until I get to the point 5, in which case I've got a break in the graph, which means that the function is not continuous over the entire real system. Okay, I'm going to skip number 2, leave it just for a second in case you want to try it. It's very similar to number 1. And I'm going to move on to number 3. Number 3 is broken up into 3 pieces. The first piece, x squared minus 2x, is going to go from -1 to 2. And so my x value, I know that's not the function, but that's where my x values belong. The second function is going to go from 2 to 4. And the third function is going to be everything after 4. I just put that there so you can kind of see where my graph is supposed to be. Let's look at the first function, x squared minus 2x. That's a quadratic function. I can leave my quadratic in what is now standard form, and I can do negative b over 2a to figure out what my vertex is. But on these particular problems, I kind of like to put it in intercept form if it's easy to do so, and this one is. I can call x squared minus 2x by factoring out an x times x minus 2. That tells me that I'm going to have a 0 at 0, and I'm going to have a 0 at 2. And look at that, both of those are in my domain, so both of those zeros will be there. In fact, I'm going to put them down. 0 is equal to x, and 2 is equal to x. I may have some other ones coming up a little later. We'll see. Those are my zeros of the function. Okay, now, if I have a 0 at 0 and a 0 at 2, my axis of symmetry has to be between 0 and 2. So I have this axis of symmetry at x equals 1, and the x value of my vertex, it's got to be, the x value is 1. How do I find the y value? Just plug it in. 1 squared minus 2 is negative 1. I have a vertex of this function at 1, negative 1. Now I've already got one of the endpoints of this function I see is the point 2, 0. I'm going to go ahead and label 2, 0. I'm going to go ahead and label 1, negative 1. However, the other side of this function begins at negative 1. So let me plug negative 1 into the formula. If negative 1 squared is negative 1 times negative 1, which is 1, minus 2 times negative 1 is plus 2. And so at negative 1, I'm going to get a value of 3. Remember, this is a quadratic that opens up, but the only parts of this that I'm looking at are this piece right here. And I've taken care of this red domain, as I call it. That's the first little backwards looking j. That's the piece of the quadratic that gives me this first piece of my piecewise function. Now the green part, 2x minus 1, going from 2 to 4, 2 non-inclusive and 4 inclusive, well, that's a linear function. It would begin at negative 1. Let me throw a little color in here. It would begin at negative 1. I have a slope of 2, so I'm going to go up 2 over 1, up 2 over 1. And look where my first point is. My first point is going to be at 2, 3. That really wouldn't have been too hard to find, because if I had plugged in 2 into the formula, 2 times 2 is 4, 4 minus 1 is 3. Now, why did I put an open circle? Because it's 2 is less than x, not 2 is less than or equal to x. What's my value at 4? Well, if I plug a 4 into this value, 2 times 4 is 8 minus 1 is 7. So I should also have the point 4, 1, 2, 3, 4, 5, 6, 7 on the graph. And this is linear, so I'm going to connect these two. Here is the point 4, 7. This is the point 2, 3. Why did I put a closed circle on 4? Because it's x is less than or equal to 4. And from here on out, the graph is going to be equal to 3. So I go back to this 3, put an open circle because it's only for x is greater, let's draw it like that, only for x is greater than 4. And the rest of the graph is going to be that constant function, y is equal to 3. So here's what my graph looks like. It's broken up into 3 pieces. What is f of negative 1? F of negative 1. Negative 1 belongs to the first function. If I plug in negative 1, I think I already did that, I get the value 3. And so I've got the point negative 1, 3 on the graph. What is f of 3? Well, let's look at these 3 domains over here on the right-hand side. Which one of these does 3 belong to? Oh, well, it's between 2 and 4. I should get 2x minus 1. 2 times 3 minus 1 is 5. And so the point 1, 2, 3, 1, 2, 3, 4, 3, 5, Very good, it's on the graph also. So f of 3 is 5. And finally, what is f of 6? Well, which one of these three domain pieces does 6 belong to? It's greater than 4. It must belong to that one. The point 63 must also be a point on my graph. And it is, so I'm feeling pretty good about the way my graph looks. Okay, I found the zeros of the function. I found these two. You can easily look at the graph and see those are the only two zeros of the function. So I'm finished. What is my y-intercept? Well, if 0 is a 0, then my y-intercept must be the origin, 0, 0. What's the range of this mess? Well, look, it starts at, whoa, what was that? It starts at -1, and -1 is included. We have a little bit of trickiness up here at 3, but 3 is included, and then it continues up until I hit 7. So the range of my function is going to be from -1 included to 7 included. And clearly, this is not continuous over the entire real number plane. I am going to skip number 4. You can work it if you want. You can see it there. I'm going to go ahead and work on number 5. Okay, number 5 is broken into two pieces. The first piece is all the numbers that are less than -1, for that matter, less than or equal to -1. And the second piece is all the numbers that are greater than -1. You sure don't have to put those lines on there. This is just trying to give you an idea of what I'm doing. The first piece of my function for all values less than -1 is the absolute value of x minus 5. The parent function of this is the absolute value of x, which makes a v at the origin. I've taken this thing and I have moved it right 5. And so I'm going to do that. I'm just going to take this graph and I'm going to move it 5 right, and then it's going to make a v from here. And I'm not even going to draw this very much because it's not part of my domain. Right? However, this side is, and I'm going to be real careful till I get to the point I'm supposed to be, which is -1. Looks like I'm going to be at -1, 6. And then it's going to continue on. It actually just looks like a ray from there. The rest of this stuff is not part of my graph because it's not part of my domain. And so my absolute value function actually ends up just looking a little bit linear, has that point -1, 6 on the graph. From there, I have this rational function, 1 over x plus 1. I'm going to put a few more little extraneous pieces on here so you can see what I'm doing. The parent function for this graph is 1 over x. And what have I done with the 1 over x graph? I've moved it 1 left. 1 over x graph normally, well, in fact, still has a horizontal asymptote at y equals 0. How do I know that? Because it's bottom heavy. The degree of the denominator is bigger than the degree of the numerator. And so whenever you're bottom heavy, your horizontal asymptote is going to be y equals 0. I have a vertical asymptote. To find my vertical asymptote, or at least my point of discontinuity, I set the denominator equal to 0, x equals -1. Remember, my original graph was going to have a vertical asymptote at 0. It got moved 1 left. And so I now have a vertical asymptote at x equals -1. I don't know that you need these pieces. It's just going to help me graph. Remember that you've got all this stuff down here that's going to be part of my graph that I'm no longer going to use. However, the rest of this graph I am going to use. And let me just look at a few points real quick to make sure I'm doing this right. At 0, I'm going to have the point 1. Why? Because when I plug 0 in over here, I get 1 over 1, which is 1. At 1, I'm going to have the value 1/2, so I have the point 1, 1/2 here. At 1/2, I'm sorry, at -1/2, I'll have 1 over 1/2, which is 2, and so I'm going to have a value -1/2 too. And I think you can pretty much see from here the graph is going to head up towards infinity as x approaches -1 from the positive side, or the higher side, and then it's going to come down here and get closer and closer and closer to the line y equals 0. Don't let this bump fool you over here. It really is heading towards 0. We'll never get there this side of infinity. All right, so let me get rid of this stuff here that's not part of my graph. I probably can even get rid of some of these asymptotes here, but I'm going to leave this other one just so you can see what's going on with the graph. I hope that makes sense. Now let's look at some points. What is f of negative 3? Notice I could have done this first and gone back the other way. And if I look for negative 3, well, that belongs to this formula, correct? And so negative 3 minus 5 is negative 8. The absolute value of negative 8 is 8. And so at negative 3, I should have 1, 2, 3, 5, 6, 7, 8, right? Negative 3, 8 is a point on my graph. The point at 4, 4 is greater than negative 1, so it's going to go here. At 4, I would get 1/5. And there's my graph over here. Notice I ran it a little high, but it should be for 1/5. I do want to put this point here, make sure that negative 1/6 is there, which is the one endpoint in my graph. The other one doesn't have an endpoint because it's heading up to positive infinity here. The zeros in my graph, well, I never cross the x-axis, not applicable. The y-intercept, I better have a y-intercept if it's going to be continuous, or if the domain is going to be all reals, which I didn't put yet, but I will now. Look, I use every single x value, so the domain is all real. It does have an x-intercept. 0 is greater than negative 1, so I plug in a 0. I think we already had that point. 0, 1. Okay. The function is sketched. What's the range? Well, I'm not going to quite make it to 0, but I'm going to be as close to 0 as I can. And I go up to infinity, so my range goes from 0 to infinity, where 0 is not included. And once again, this function is not continuous over the reals. I'm going to skip number 6. You can try it on your own if you would like. It's there for you. All right, now I want to write in a piecewise function for the graph. I'm going to skip this one because it looks like two linear functions. Doesn't seem that difficult. Let me go to B and see if we can write a piecewise function. Now you have two ways to look at this. You can look at it like it's 4 pieces. 1, 2, 3, 4. Looks like a linear, constant, and a linear. But I think I'm going to write it instead as just 3 pieces. I'm going to write it as an absolute value, and then a constant, and then a linear. Okay. Now, what I want to do with this is I want to make sure that I get my pieces correct, and so I'm going to start off with f of x is equal to, and I'm going to have 3 pieces. The first piece goes from negative infinity to negative 2. So x has to be greater than negative 2. I am fibbing. X has to be less than negative 2, of course. Now, why is it strictly less than? Because I got a hole. You see this hole here? So my first function is going to be x is less than negative 2. My second equation is going to go from negative 2 to 0, and both of those are inclusive. So 0 is less than x is less than 2, and they are both inclusive. Less than or equal to, less than or equal to. And then finally, my third one is going to go from 0 to infinity, so I'm just going to write that as x is greater than 0. All right, this absolute value function, look, it's got a slope of 1, so I know it's y equals the absolute value of something. Well, this is the absolute value of x moved 4 to the left, so I can write that as y is equal to the absolute value of x plus 4. I just took my absolute value function that used to look like this and moved it 4 to the left, and that's what I end up with. The second piece of this is even easier. Look, everything's 4. So it's 4 from 0 to 2 inclusive. And then the last one is also just about as easy because it's a linear function. The slope is up 2 over 1, so I have a slope of 2 and a y-intercept of negative 3, and so I can write this one as y is equal to 2x minus 3. And there's my piecewise function. Hopefully that wasn't too bad. Let's see, I think I will do one more. Let's look at this thing. It looks like it's broken into 2 pieces to me. This piece looks to be quadratic, and it seems to be followed by a linear function, and so I'm going to write it that way. This time when I do my f of x, I'm only going to break it into two pieces. The first one is for all x's less than 0. I'm going to put less than or equal to because they both end up in the same place. It doesn't matter where. I want to make sure that I account for the point when x is equal to 0, sitting there at the origin. And then I'd have a linear function coming from there where x is greater than 0. 0 was accounted for in the top function. Once again, hopefully you can see that as I go over 1, I go up 1. As I go over 2, I go up 4. That means that I'm going to have an a value of 1. What am I talking about? Remember my parent function, y equals x squared, looks like this. What did I do with that function? I moved it 1 left and 1 down. Okay. So how do I move that function 1 left and 1 down? I'm going to say y is equal to, did I put x squared there? I don't remember. 1 left is x plus 1 squared, and 1 down is minus 1. Now you may not be real sure about the a value, so let's check. Y is equal to some, let's make sure I know my scale factor is right, because I know my vertex is right. I'm sitting here in vertex form with a vertex of -1, -1. I've clearly taken care of that. I need to make sure it works, so let me plug in a point that I know works, 0, 0, and I'll get 0 is equal to a times 0 plus 1 squared minus 1. 0 is equal to, well, 0 plus 1 is 1, 1 squared is 1, a times 1 is a, 0 is equal to a minus 1, so a is equal to 1. Just double check, and sure enough, this is my equation. Y is equal to x plus 1 squared minus 1 for all values less than or equal to 0. Then I have a linear function. Well, look, my y-intercept is 0. My slope is -2 over 1. So this is just going to be the graph y is equal to -2x. Hopefully those weren't too tough, and hopefully you get an understanding of what's going on with piecewise functions, and I'm sure you will get a chance to do more as time goes on.